Good morning, professors, teachers, and my fellow students. Today, I will give a presentation on our research topic, illumination problem. Our school team number is 60391. Before I start, I have a question. What is the best arrangement for 6 bulbs of equal brightness in a circular room? You might think of a regular polygon. Maybe, but surprisingly, no. And the details I will discuss later. First of all, let me define what is the best arrangement. We define a set omega in R2 to represent the room, and there are n light bulbs alpha k, and the light intensity upon P after normalization is given by this formula. And then, taking minimum over the omega, we have the minimum intensity point in the room. Our objective is to find the positions of the bulbs to maximize the minimum intensity points in the room. Because in the following, I will go through the circular room, 3D generalization, and finally the rectangular domain. Because there are many ways to arrange the bulbs, we have 2 assumptions. First, the arrangement of bulbs is symmetric, since the room or the domains we considered are symmetric. Second, more minimum intensity points will be the best arrangement, because we believe that the light intensity should be more evenly distributed. To start with, let's consider a circular room of unit radius. We arrange the bulb in a regular polygon like this, and each bulb of distance x to the center of the room. First, we simplify the IN for n equal to 3, 4, and 6. And we guess there should be a general formula of it. So, we conjecture this formula and check it numerically for n equal to 5. To prove it, we use compass number. That means we transform the problem to find the summation of 1 over square of modulus of alpha k minus 1, where alpha k are the roots of the equation and also the positions of the bulbs. We use the substitution, and then our problem is need to find the summation of square of modulus of beta k, where beta k are the roots of this equation. We now have general formula to find the summation of beta k and summation of square of beta k, but we have no idea how to find the summation of square of modulus of beta k. Fortunately, under the assumption that if beta k lies on a circle, we have a formula to find it, where r is the radius of the circle, and w is the center of the circle. We now have proved this equation for the intensity at the minimum points for a regular arrangement. More generally, we can find the intensity at any point in the room. Okay. For n equal to 3, 4, and 5, that means we have 3, 4, or 5 bulbs. By differentiating the intensity, we find out the size of the regular polygon we arranged for the bulbs. And these are some figures. Okay. How about for n equal to 6? By using Excel, we find out that the value of x will increase with number of bulbs. And at the point, the minimum intensity at the center will larger than the minimum intensity at the boundary. This means that our previous arrangement is no longer the best. We then have 3 new proposals. First, decrease the value of x such that the minimum intensity point on the boundary will equal to that of center. Second, we put 1 bulb in the center and arrange the others to form a regular pentagon. Third, we arrange the bulbs in 2 equilateral triangles with different distance to the center. And by comparing the intensity, we can find out that the third one is the best among those. And this result also prove that, or also showing that our second assumption, that more minimum intensity point is better, is not generally true. For n larger than 6, we can even predict that the layers for the bulbs will form a more complex model that is far beyond our knowledge and ability. So we have to move to a 3D room we live in. The intensity at the point P here is shown by this sum. And in order to use the previous result, we use a substitution for the denominator in this form. And by expanding it and comparing the coefficients, we get the A and W dash in terms of W, X, and H. And finally, the intensity at point P. Okay, let's have a quick review on the circular domain before we move to the rectangular domain. For 1 or 2 bulbs, they are located in the center. And for n equal to 3, 4, and 5, they are arranged in a regular polygon. And for the case of 6 bulbs, we form 2 equilateral triangles with different distance to the center. Let's move to a rectangular domain. We assign the room in this. The length of the room is 2a, where a is large or equal than 1, and the width of the room is 2. Here is the summary of the rectangular domain. For n equal to 2, we made a mistake here. There are only 1 cases we need to consider. We have to set the intensity at the 4 corners equal to that of the midpoint. And then we get an explicit formula for x in terms of a. And for n equal to 3, there are 2 cases. When it is small, we only need to maximize the 4 corners. And we also get an explicit formula. But however, when it is large, there exists a local minimum on the long edges. And we have to set the corners intensity equal to that of the local minimum. And then we get a polynomial equation for x. For n equal to 4, there are totally 3 cases. And it depends on the value of a. When a is small, we arrange the bulbs into a rectangular shape. And we set the intensity at I1 equal to I2 and I3. For medium A, we arrange the bulbs along the x-axis. And we have to maximize the corners intensity subject to the constraint that the intensity here equal to that of the midpoint on the long edges. And for large A, there exists a local minimum in the long edges, and we set this phi intensity the same. And it is very interesting for A equal to 2.28660, because the solution in it is not unique. We can either put in a rectangular shape or along the x-axis. This example has shown that the solution of these problems is not unique in general. And we think that several problems need further investigation. First, the situation of more bulbs. We even cannot predict or how to arrange the 7 bulbs in a circular room, and how to prove the results. We cannot prove the results for n equal to 3 in a circular room because we have many choices, or we cannot find out the infinite minimum intensity points. And 3 generalization, different domains like a rectangular room, how to solve mass mean problem in general, and does there exist any non-symmetric solution? We don't know. Finally, we hope that our research will be helpful in future. Thank you.